Welcome back, ladies and gentlemen. Let's carry on with this kinetics, and we were essentially discussing differential rate laws. I hope you've watched the first part of the video, or you're coming in the middle and maybe a tad lost, unless your teachers taught you this in class and you're just doing this for a review. But either way, my name is Renee McCormick. This is a Dallas, Texas twang that you hear, and I am so glad that you have joined me. All right, so we had just finished introducing the idea of table logic and ugly algebra to be able to analyze data. So we're going to carry on with that and do, I don't know, about half a dozen more examples until you get good at it. It's not an excuse for you not to be good at it. All right, so if you have a case in your data tables that you're looking at, and again, what kind of data tables would they be? The headings would say concentration and rate, as opposed to concentration and time, which will be yet another recording with a different kind of rate law called integrated rate law. But I digress. If you have a case where one reactant is never held constant, then it's a rut-row moment. You know that beautiful scientific phrase from cartoon land. Rut-row. We're in trouble now. Then you can either add an expect column to the table, which is easy enough to do. I'll show you some examples where we can do that. Because you can usually determine the order of at least one reactant, if not, if they're more than one, then, or more than two, then usually you can get two out of the three. And you can predict the expected change in rate and then proceed as usual and compare your expected rate to the actual rate for doubling the concentration of the other reactant, etc. I know it sounds like gobbledygook until we do it. Or you could just plug into ugly algebra. Just use the method that makes the most sense to you. You just got to be quick and accurate. So if you're prone to algebra mistakes, table logic is probably the way to go. If you love algebra and you are fast as lightning at it, then that's the way you should go. All right. So here we have a very scary looking thing. Pentamine, cobalt, Roman numeral 3 chloride. I had to think all that through. That's another lesson. That's going to be covered in the net ionic recording on complex ions, how to name them and such. It's actually kind of fun. Anyway, whatever this thing is, just think of it as A. So this reactant plus water yields this big, giant, hairy, ugly complex, and the whole idea was to get that chlorine out of there. So that comes out as chloride. I think that probably has 2 on it. It's just a chlorine atom at that point. It's very odd. But what we have is a rate law in the form of rate equals K times this big, hairy thing we'll just call A for simplification. We are looking for that exponent, M. So I've got initial concentrations on this side, right here, and I have rates over here. Note the units on the rates. They're molarity per minute. So when my K value has got to carry the minute, and then it's a matter of how many other molarities does it carry. All right, so to get started here, this is easy because I only have one reactant that's participating in this. And you also can ignore all of these because they're the same, so you can just focus on 1, 2, 3, and 1. And you see that that's just kind of silly. That stays the same, so go figure. If you don't change anything, it stays the same. But if I double the concentration of the reactant from 1 times 10 to the minus 3 to 2 times 10 to the minus 3, the rate doubles. So if I double this, the rate doubles. If I triple it, the rate triples. So it's first order. So rate equals K concentration, and because it's in square brackets, we put curly Q brackets, which I don't draw very well, sorry about that, outside of it. So cobalt, 5 ammonias, but when they are in this position, we call them ligands. Again, that's a whole other lesson. Cl, 2+ ion, and pretend that looks like curly Q bracket. I think I could do a little better than that. There we go, that's better. Where they want us to find the value of M. So outside these curly Q brackets, we just discovered it was first order. So I put a 1, or leave it blank implies a 1. And calculate the value of K. So K would equal, pick a line, any line. It's going to equal rate divided by the concentration of all that gobbledygook to the first power. So I'm going to go with, I'm just going to call this A, just to simplify things. And you could do that on the AP exam too. Kids always ask me, can I do that shortcut? Yes, you can, because you don't have the precious seconds to waste writing all of that mess down. So I'm going to just stick with the top line, 1.3 times 10 to the minus 7 divided by 1.0 times 10 to the minus 3, and I suspect that's going to come out 1.3 times 10 to the minus 4. If you want to get a calculator, double check me. You're more than welcome. But I'm pretty sure that that's going to come out 10 to the minus 4, and that's going to come out 1.3. Question R, what are the units? Well, since it's first order, we're covered on the molarity because it's going to be multiplied by this curly Q bracket stuff, which is my molarity. So all I have to do is put the time unit down here, which is minutes. Just don't get creative. Make sure you always look back at the data table and put the proper time unit. All right, this one's more exciting. Change color. The reaction between bromate ions and bromide ions in acidic aqueous solution is given by this equation. The table below gives the results of 4 experiments. Using these data, determine the orders for all 3 reactants, the overall reaction order, and the value of the rate constant. So what is the value of K, and what are the units of K? Well, we just got to pick a place to start, don't we? Since we have 3 reactants, which is not something we've practiced yet, and the other thing you want to do is you want to always eyeball the rate table. And varying exponents, always trouble. So change that one. You could change the other 3 if that made you happier, but I'm lazy. I'm just going to change the 1. That's going to be 0.80 times 10 to the minus 3. So now I can really just focus on 0.08 versus 1.6. I already see some simple relationships, and I know you do too. Not 0.08, 0.8. 0.8 is what I meant to write. If you've been listening to many of these, you know that's my worst habit in the whole wide world. So 0.8, and 0.8 twice is 1.6, all times 10 to the minus 3. 1.6 twice is 3.2. I'm feeling a pretty easy analysis coming on. So let's get started. This jumps off the page at me. I want to find a spot where everything's held constant but one of these 3 critters. So doubled, and I got the number 2. I like that. What did the rate do in response to that? It doubled. So we know this is first order. Whatever thou does to the concentration, if that same thing happens to the rate, then you're first order. That one wasn't too painful. It's going to get worse. Okay, let's see. What do we got next? I really want to focus on that middle bromide. So what can I use? Oh, the middle 2. Okay. Sometimes it takes a minute to see it. For experiments 2 and 3, concentration of the bromate ion and the H plus ion is held constant. I'm going to get rid of that blue box. What happened then? Going this direction, this doubled. What did the rate do in response to that? It also doubled. Agreed? 1.6 twice is 3.2, but you can ignore this part since they're all the same. So that's also a first order. So we're doing good so far. Now, I've got to use this bottom line because it's the only place where hydrogen is anything other than, the hydrogen ion is anything other than 0.1. So what lines should we choose? It's looking like the bottom 2. These are staying constant, which is a good thing. What's going on there? Doubled. What's going on there? Nothing. What do you mean nothing? How's that possible? Is that right? I don't think so. I'm looking at something wrong because that's supposed to be hold on. I'm going to clean everything up. Let me try that one again. I don't think that's right. That doesn't feel right. All right. Looking at hydrogen, concentration the same, concentration the same. I picked the wrong lines. Sorry about that. Okay, so those are the same, those are the same. What's going on here, from here to here? That is doubling? Yes? Yes. So that is doubling, and what is the rate doing from this 0.08 all the way down to there? That is quadrupling. 4x. So that means this is second order. That feels better. I knew it couldn't be 0 order just from looking at the rate data. All right, so sometimes it takes a couple tries, huh? So rate equals K, concentration BrO3 minus to the first. And again, you don't have to write that one. I just do it for emphasis. It would be perfectly acceptable if you just stop at writing the brackets. This one, however, is non-negotiable. H plus second order. What is the overall reaction order? Not a trick question. Go ahead. 2 plus 1 plus 1. 4. And the value of the rate constant, K equals the rate. Pick a line, any line, just stick with the same line. Concentration of this. Concentration of this. I left my minus sign off. Concentration of this squared. So I'm going to go with the top line. 8 times 10 to the minus 4. And that is in molarity per seconds, divided by 0.1. I'm going to lead off my 0 there. 0.10. Those are both to the first power. 0.10 to the second power. And that is going to be, that's 10 to the minus 2 times 10 to the minus 1 times 10 to the minus 1. Isn't that 10 to the minus 4? Yes, it is. So this whole denominator is canceled out by that, and I come out with 8.0. You can use a calculator if you feel better. And this, when you do this, that's 4 molarities. So that's m to the 4th. So only one of those is canceled off, so it's m to the 3rd. So the units on this are molarity cubed dot second. Okay, there's many ways to write this. Different books write it different ways. Even the AP exam sometimes writes it different ways. So let's just talk about all the different ways grown-ups don't get along. 8.0 everybody agrees on. So I could call that mole per liter cubed seconds. I could call it mole cubed liter minus 3 seconds minus 3. I could call it, oh, that's not mole cubed, liter cubed. Sorry, I got that upside down. Liter cubed, mole cubed. Because they're inverse molarities. Did I do the rest of it right? Nope. So it would probably be written, well, it might be written this way. These are commutative, so. All right, but I'm a fan of this way because it's not as confusing to me. Now, maybe you guys are better at that other stuff than I am, and that's quite all right. So I'm going to let you in on a little secret. This unit thing looks way more complicated than it needs to be. Let's just recap. K has to have a number. Must be a number in numerator. And time in denominator. So the question becomes, how many ohms? Well, it's an easy little trick. Are you ready for the trick? I don't give you a lot of tricks, but here it goes. What is the overall order? 4. I always told my students, literally, humor me. I realize this is very elementary, but humor me. When you get that overall order, put 4 fingers up. It's 4. Put up 4 fingers. Drop a finger. How many fingers are you looking at? 3. So that's why there's 3 molarities, because one of them's going to get canceled off. So 3 molarities in the denominator of the number 8, in this case, times the time unit of seconds. Where did that come from? Look at the table. Look at the table, eyeball the table, grab that second, and put it down in that denominator with it. If you just report it like that, it's a lot simpler. All right. Several more practices coming at you. I'm going to do another recording after this because I know you just love listening to them. For those of you that need more help with all the different components of AP problems, once I have finished doing the rest of this chapter, but I just kind of wanted to stop right now and focus on just these tables of data and repeat until you're happy. So I'm going to do 4 of these tables, and if that doesn't make you happy, then you need to go to the where I'm going to work through all the worksheet problems, which I'll have some of these done again that way, and you'll get to hear it again, and you'll get to see all the other pieces worked, but this is where we are going to start. So we're starting here at this 1981 problem and looking at this equation. So I'm going to come out with something like this just by looking at the equation. Reactant A, reactant B, and I'm in search of what those exponents are. So of course they give me initial concentration of reactants, moles per liter. They put the units up there, so that's why these are not in square brackets. And they put the little zeros on them for initial or original. And then they gave me the rate of the reaction, and my time unit is hour. So I encourage you to do what I do. And I encourage you, the way I encouraged my own students who are ever so successful, to circle bits on the page that are going to help you later, so you can just glance up there and go, what was that time unit? Oh, it's in the circle, it's an hour. So you can go a lot faster this way. All right, so what am I looking for? I am looking for either A or B held constant. And if I get what I really want, I want also A held constant and a relationship of doubling, or 2, if I get what I really, really want. I found it. I found the one I want. It may not be the only one there, but I did find the one I want. So I'm going to go with experiment 2 and experiment 5, which both hold A constant at 0.24. And then I'm going to go this direction because 0.06 twice is the number 2. So that's my doubling that I like. It's just a personal preference. I must go again from 5 up to 2. You can't get creative. Notice everything has been line 2, line 5. And what happened as a result? Also doubled. Yippee skippy. That means it is first order in the thing that was changing, so it's first order on B. All right, now same song, second verse. In a well-designed experiment, what was just varied is somewhere held constant and vice versa. So I'm looking at those lines. I like that one. I like that and that, which makes me go from here to here. That's a doubling in that direction. And so I go from the same spot from here to here, and that's a quadrupling. So how do you get doubling to equal quadrupling? You must square it. So again, what you want to be thinking about is when I say the concentration of B is doubling, and this concentration is being held constant, so it's going to be a 1, and then that's going to equal a K times 4 rates. The only way to get a 4 out of a 2 is if that was squared. So this is going to be second order. So once again, while we hold in purple, experiments 2 and 4 hold the concentration of B constant. Experiment 4 up to 2 doubled the concentration of A. The rate quadrupled as a result of doubling A, which is 2 squared. 4 is 2 squared, so that means I need a 2 on that A term. So the next thing we would be asked to do, you can just bet these all follow the same recipe. We're going to be asked to write the rate law. Easy enough. Rate equals K. They all start that way. Don't forget the K. A, that's why I like to write it in the table too, because now I just look at it. A we determine was second order, B is first order, and then they want me to solve for K. So K is going to be, with proper units by the way, K is going to be equal to rate divided by A squared. That is a really ugly A. That's better. B. I'm going to put in actual numbers here in a second, but I'm going to come out with a number. It's going to have the time unit of hour in the denominator, and ask yourself this question: what is overall order of reaction? Are you smarter than a fifth grader Jeff Foxworthy math? 2 plus 1 is 3 is the answer. Therefore, put all 3 fingers up, drop 1 down. You're looking at 2 fingers. That's 2 molarities. So that's going to be its units. I've still got to get all that other gobbledygook in there, so I'm going to scoot that over. We just decided it was molarity squared hour. Pick a line, any line. I'm going to go with the top line. At least they made nice numbers without a whole bunch of times 10 to those. So 8 moles per liter per hour. I already know what these are going to be, but we'll go ahead and do it. Molarity per hour. And then this is going to be molarity cubed, these terms that once we multiply them together, which is why K has got to have that unit on it. And so this is going to be, erase that for a second. What is A? A is, what line am I using? I've already forgotten. First one, 0.24, quantity squared, 0.48 quantity to the first. Bad form not to put my zeros in, but they mess me up, so I do them last. That is a real zero. All right, calculator time. 8 divided by, open a paren. Don't you love your parentheses keys by now? Got an x squared button to make that squared. Times 0.48, close a paren, whole bloody mess. 289. How many sig figs? 289 it is. Thought maybe it'd round to 290, but nope, 289. So that's going to equal 289. And we already determined the units. Third order overall, drop a finger down, molarity squared, dot, what was the time unit? Hour. Now, if you need to see it, this is molarity cubed, isn't it? Because square bracket squared is molarity squared times square bracket, which is molarity cubed. So that cancels down to a second. That's gone. And this pops down here. It's a per hour. So there you go. That's where it comes from. So that is typical of an AP problem. So let's get this recipe down. Determine orders. Write rate law or rate expression. Solve for K. Give units on K. Many other things we can ask to be do from there, but this is the recipe that almost all of these start out with. Embrace it, master it, learn it. You're going to be making good grades in this unit. And like I said, I'm not working the rest of this problem. I didn't even put it all on here. I just want to practice this skill until you're good at it. As soon as you're good at it, for the love of God, shut me down. Turn me off. Put me away. And just move on with your life. All right. Again, I'm looking at data. Oh, that's big trouble. That's trouble. You know that the next piece of this would be to find out what that was using the stuff we find. Okay, so let's give it a shot. What do we have going on here? All right, I've still got enough to get going. I like this, and I like this. Now, you don't have to like that. You can go the other direction. I like this way. I'm driving this bus. I get to do what I want. So, holding the concentration of HgCl2 constant, the concentration of my favorite polyatomic ion, oxalate, doubles. I'm asking myself what happened. Well, what happened is a quadrupling. Thankfully, these are all the same. You always want to look for that. These are all the same. So I can focus just on this over here, and I'm betting that 0.52 times 4 is exactly 2.08, but even if it was roughly 2.8, I'm still going with 4 times. Because, you know, this is real data. Well, okay, maybe they didn't. But if it were real data, you got to have a little wiggle room in the exactness of the 0.08 versus 0.07 versus 0.09 versus just 2. All right, so that's 4 times, so that means that this is second order, because the only way 2 is going to be equal to 4 rates is if that exponent is a 2. All right, what next? Well, I don't have a lot of choices. Here we go. Ooh, I found my doubling. You don't always find it. We haven't run into one yet, but you don't always find it. But what's going on here? Well, that's weird. This was doubled, but that appears to be cut in half. Is that what you would say? That's doubled, but yet that's cut in half? Very strange. No, it's not. It's doubled. I'm having a math retardation moment. 1.06 times 2 is 2.08, McCormick. So, indeed, it's doubled. All right, so that's going to be first order. So, rate equals HgCl2. I shouldn't do 2 of these recordings in a row, should I? C2O4, 2 minus, squared, peachy. Overall order. Again, let's follow the recipe. This is the things that you almost always will ask you. What's the overall order? 3. It's third overall. Therefore, K's units are, again, 3 fingers in the air, drop 1, molarity squared, dot, minute. So, calculate K. K, bad form. K equals rate divided by HgCl2 C2, that's not CR, that's oxalate, C2O4, 2 minus. And kids always ask me, do I need to write that? The answer is you oughta. And the reason you oughta is if you goof up and you put the numbers in wrong, then you're going to miss all the points. But if you put this in correct, sometimes the grading standard gives points just for that and not even for the real answer. They want to know if you know what you're doing, not that you can drive a calculator. We're pretty sure you can drive a calculator, but do you understand the setup of how these relationships work? So pick a line, any line. I'm going with 0.52 times 10 to the minus 4, but you can use any line you wish. And that is molarity per minute. Partition that off. And then I'm going to put in this value from that line, which is 0.0836 and 0.202. Don't forget to square it. Therefore, K equals, clear my calculator screen, 0.52 second EE minus 4 divided by, open a paren, 0.0836 times 0.202, quantity squared, I love the x squared button, close the paren, equals 0.15. Double check and make sure that's right. Yes, it is. I love it when I get the right answer. 0.015. And we already determined its units. It's m squared minute. If you don't like the fraction thing, 0.015 m to the minus 2 minute to the minus 1, if that's how your book does it. Put it in any form, any equivalent form you would like. I won't be mad at you. I'm going to give myself a little more room because that's looking pretty messy. All right. Again, everybody's capable of doing this. It just is a matter of repetition. Some people get it after 1 or 2 repetitions. Other people need 4 or 5 or 6. There's nothing wrong with getting a new piece of paper and starting this all over again and starting from scratch. I would sleep once just to let your brain reset, but there's nothing wrong. You can do this if you want to. All right. Look, they're trying to trick me right off. How come? Because most of what we look at has rate as the last column. This one has rate in the beginning, but it is in times of seconds. And it is, they're trying to trick me again with the exponent business. So make this 0.7 times 10 to the minus 3. And I can ignore all of this and focus on 0.7, 1.4, 2.8, 4.2. I'm looking at multiples of 0.7, aren't you? Yep. This one's not going to be too bad, hopefully. So I need to find a place where something was held constant. Oh. Right there. And I'm going to go this way because you already know me. I'm a fan of the number 2. So that's a doubling. So I asked myself what happened here. And it's also a doubling. So the thing that was changing is y, and it's first order. But now I'm in trouble. New skill. The new skill is that crap. They did not design this well. They never, ever held y constant. But you know what? You know how y behaves. So you can write an expect line. Or you can do algebra. I'll do this both ways for you. I'm not as good with the algebra, but I think I can make it happen. All right, so I definitely don't want to use the same 2 lines because I need x to change. And I'm going to choose just the top 2 because my math over here is pretty easy as well. What do we know? We know that this initial rate of 0.7 times 10 to the negative 3, 0.70 times 10 to the negative 3, that's not very pretty, is going to double. How do we know that? Because we know that whatever we do to the concentration of y also happens to the rate. So if this was 0.70 times 10 to the minus 3, by the time it gets here, it's going to be 1.4 times 10 to the minus 3 anyway, just because that doubled. So I mark through this and I say I expect, just because I doubled y without even looking at what x is doing, this is going to become 1.4 times 10 to the minus 3. And that's what I compare to 1.4 times 10 to the minus 3. So I doubled x, didn't change the rate at all. Everything that happened because we already knew how y was behaving. So that's zero order. I know you are not convinced. I'm going to pick a different line. I'm going to convince you. This is still going to be 0.7 times 10 to the minus 3 for ease of comparison. I'm not going to use those lines. I'm going to come out of my comfort zone, and I'm going to use these lines just for fun. Oh, bad decision. That's a bad decision. That's going to make too much work. Let's use this. I can multiply by 6 easier than I can multiply by a fraction. Better yet, can I change my mind a third time? Because, women do that. I'm going to do this one. That's 4 times increase. Agreed? 0.1 going to 0.4. So this is not going to remain 0.7 times 10 to the minus 3. It's going to become 4 times that before I even get out of the starting gate with whatever's happening to x. So 4 times 0.7 is 2.8. So I have this expectation already. Now I get down to what's really happening here in the same line from 1 to 3. They didn't number them for me, but we can tell that. And this doubles. So now I'm comparing this number to this number and asking myself what happens. Well, dang it, it didn't change again. So I'm standing my conviction that it is zero order. It does not matter what I do to x. It's having no effect on the rate. So rate equals k concentration of y. And that's that. That means that the units on k, well, the overall is 1. Therefore, no molarities on k. K is simply going to hold a unit of the time, which is a second. So it's going to be the number per second. No molarities in the denominator. So k is equal to rate divided by the concentration of y. Pick a line, any line. I'm going to go with the second line, 1.4 times 10 to the minus 3. And that is molarity per second. It's always a molarity per time for rate. Always, 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 always. I say always very often. Let me say it again. Always, always, always. Over the concentration of y. And I said I picked line 2, so that is 0.20. And that's a molarity. And now we see why these cancel, and we see why k is only a per second. But we already knew that. So that is 1.4 second e minus 3 divided by 0.2 is 0.007. Somebody had a sense of humor when they wrote that problem. Seconds to the minus 1 or over seconds, however you would like to report it. But that's the k value. So it is first order with respect to y, zero order with respect to x. When I do the actual AP problem sheet recording, we'll worry about how we write the sentences to explain that or this or that. All right, then I promised you I would also do this in ugly algebra. So I need to hold true to my promise. So clean this up for a minute so you can see how it starts. Okay, clean slate. So let's try this again. Ugly algebra. Just pick 2 lines. Which lines would you like to choose? Do you remember our hint? Our hint was you're going to do less math if you'll pick a place where something was held constant, anything, and the rate changes all the way down, that holds constant there, that changes all the way down. This would be the 2 I want. I want these 2. Because I don't want to do all that ugly algebra. I want something to cancel out. That's me whining. Rate over rate. So I'm going to do 2 over 3. 1.4 times 10 to the minus 3 is equal to 2.8 times 10 to the minus 3 equals 0.4, 0.4, okay, and k. The k's will cancel because constant's constant. And 0.2 and 0.2. Cancel, cancel, cancel. Oh, this feels so good. All right, so summarizing, what's that going to be? 1.4 divided by 2.8 is 1/2. Agreed? You might want to write it as 0.5. It's up to you. 0.2 over 0.2 is 1. How is that going to happen? How does anything in this bracket raised to a power ever equal 1? Well, it's got to be 0 order. So what was 0 order? The thing I canceled out, right? Or, yeah, the x. So my x is going to be 0 order. Then you do it again, and you do it again for the y, and you should come out with first order for it. So I wanted something to cancel, and that's what I got. 1/2 equals 0.2 over 0.2. Oh, did I write that right? I might not have written that right. Hold on. 0.4, 0.2, 0.4, 0.4. Ah! Phooey. Let's try that again. Okay, so 1/2 equals 1/2. Ah, that's why it's first order. Okay. The only way that's going to happen is if that has a 1 on it. So this would have a 1, that would have a 1, the fraction overall would have a 1. So it's first order. So this was my x, that's my y. So that's first order. Now we do it again for the other one. But the problem is it was never held constant, correct? So you can pick any lines you wish. So let's go with 0.7 and 1.4. Okay. The 0.7 line was 0.2, 0.1. 0.4, 0.2. 0.7, this cancels, this cancels. 0.7 over 1.4 is going to be 1/2. And this side, you're wondering what the exponent's going to be on it, because that's the relationship with the rate. So 0.2 times 0.1 is 0.02 over 0.2 times 0.4 is 0.08, lovingly known as 1/4. How is 1/4 ever going to equal 1/2? What exponent would you have to have? Not going to happen. So you can figure that out fairly easily. Again, I'm not so great with the algebra method. Try that again, make sure I did it right. But I'm more of a fan of the table logic method. For this very reason, I get lost. All right, shall we try one more time? Experiments 1, 2, 3. This time they put the rate over here. I can already see we're in trouble because 0.1, 0.4, 0.2 was never held constant. So I'm going to have my expect line over here. And I'm going to get started by saying, I like this. That's held constant. That's quadrupled. What happened to the rate as a result? Isn't 2.4 times 4 9.6? Indeed it is. 4x. So I know right away that this is first order in F2. So I know that straight away. The problem comes in that they never held F2 constant. So I got to pick something that's easy and simple to deal with. This could give me trouble because these are the same, so that could confuse me a little bit. So I'm going to go with, but I don't have a choice, do I? Yeah, I do. I'm going to go with here and here, and here and here, doubling on 2 counts. I know what's going to happen because I'm doubling fluorine. When I go from here to here, I already know that that doubling is going to cause a doubling from here to here. So 2.4 times 10 to the minus 3 is automatically going to be 4.8 times 10 to the minus 3. Now that's what I'm going to compare to this. So that's a doubling. So what is this? 4.8 times 10 to the minus 3 versus 9.6, that's a doubling. So that's going to be first order. So rate is equal to K, concentration of ClO2, concentration of F2, both to the first power. And that means K is equal to rate divided by both of these guys. K is then equal to, pick a line, any line, 0.1, 0.01 to the first power, 0.1 to the first power. I'm using the first line if you can't tell. Isn't that 10 to the minus 3? So this comes out 2.4. Could it be that easy? This is one of those expect easy maths moments, I believe. I'm double checking to make sure I'm right. Yep, 2.4. Okay, so all of that cancels that, and we come out with a plain old 2.4. And what are the units? Come back to the original. What's the overall? That equals 2. 1 plus 1 is 2. Drop a finger. Put 1 molarity there. And what's the time unit? Minutes. No, seconds. It's right there. Seconds. And voila. So, practice, practice, practice. Sorry if the ugly algebra method part didn't work out so well, but that's why I don't do it that way. But you can. There's examples in your book you can look at, and you can practice that if that's the way that makes more sense to your brain. So I hope you have found this somewhat helpful, at least, and I will see you next time. Thanks so much.